they live wherever they want.
That's true. I want that.
You can also tie a balloon to them when they walk around in your house.
A balloon?
Yeah. Have you seen those videos?
No.
Like they have turtles and then they tie a balloon around their shell, so you just see a balloon slowly walking around your apartment the whole day.
That was great. I'm gonna do that. Right. So, can someone give me a review of what we've done in the past 2 weeks? Courtney, do you want to go for it?
It's been like about the communication protocols. I think last week it was the I squared C, and I can't remember the name of the previous one we talked about.
Okay, that's good. Who else remembers the name of the other one? Akhilesh, were you here?
This is my first meeting. I showed some interest in this topic or this field, so I'm just here to see where I fit in today.
Cool. What about John? What was the other one we did? We did 2.
I think you talked about CAN.
That's what you think?
You covered it briefly after I2C, I think.
That's a good point. I kind of snuck in a little convo in there, but that's wrong. Dead wrong. Boom.
What?
Was it UART before that?
UART, baby. Yes, Yash. Let's go. John, please. You're dreaming about turtles all day. I need you to remember.
Sorry. I have a memory of it.
Yeah, so we did UART. We kind of talked about it a little bit just because people ask questions, but I'm hoping to have an actual lesson on that, and maybe we'll get some experts to guest speak for us. But we did UART. So sort of the comparisons between these were UART is a 2-line protocol, so is I squared C. On UART you had RX and TX, right? I squared C you had serial data and serial clock. UART was full duplex, remember? What that means is that you can receive and send data at the same time. So if receive is coming in this way, I can transmit on a different line. I squared C is half duplex. And that's because you only have one pipe. You have one tunnel to send data back and forth, right? It goes on the serial data line, and the clock will toggle, and it provides a reference for how fast you should be communicating. UART had no clock, right? We only had the data lines. We didn't have a toggling clock line that comes along with us. And we called that an asynchronous protocol because the two things communicating to each other didn't have the same point of reference. They weren't synchronized. Whereas in I squared C, you have this synchronization with the clock being shared between all the people communicating with each other. Cool. Anything else? UART was push-pull, so each low and high, you could drive to logic 1 and drive to logic 0. And on I squared C, we relied very heavily on our pull-up resistors. We had a pull-up resistor on both the data line and on the clock line. And that helped us with something called arbitration, which basically solved the problem for when 2 masters are trying to communicate at the same time. So today we have SPI. It stands for Serial Peripheral Interface. I'll just type it out for the sake of very descriptive name. To be honest, I don't really understand what it means. Junaid, do you know why it's called Serial Peripheral Interface? I think people just started stringing together words to sound fancy, and this is what they ended up with. But it's not as descriptive as UART, for example, where they tell you it's asynchronous and receiver transmitter. Right, UART was universal asynchronous receiver transmitter. I2C was another dumb one, inter-integrated circuit. And then SPI continues the trend of dumb names. But essentially, the way it differs from these guys is it's 4 wires. So if I have my microcontroller, and usually we refer to these, as we learned in S2C, as a master and a slave. Not the best terminology, but the idea is that the master will always have control over communication. The master will decide when to read, when to write, and it will control any transactions that happen over this data bus. So we said 4 lines, right? 1, 2, 3, 4. And then, like always, we need to make sure we have a common ground between these two. If you have no common ground, then you don't have the same ground truth reference of 0 volts. And then you're not going to be able to communicate. Because 1 volt to the master may be 9 volts to the slave, right? If you have a different ground. They won't be synchronized. They won't have the same ground truth. So if you have the same ground, then 1 volt to the master relative to its ground will also be 1 volt to the slave relative to its ground, right? So you always need to make sure things you're communicating with share the same ground. So that's step number 1. And that's usually what you'll find is something you forget. Like if your systems don't work, like, what's going on? Like, oh, okay, I forgot to connect the grounds. That's almost rule number 1 here. And that's for everything. That's not just for SPI. That's for anything that's communicating. And anything that you're providing power for. Yeah, Mahmood.
What situations would you have when 2 PCBs have different grounds?
Look at you asking the hard questions, eh? Well, we're only 7 minutes in. We haven't even talked about the SPI lines. All right. There are a few situations. The biggest one is when you want isolation between grounds. So if I wanted 2 systems to be isolated, so I have 1 ground here, I have another ground here. So maybe I'll try like, oh, it's not a color. Try like this. There are different, I think it's the other way actually. There are different symbols for ground sometimes, but it just depends on what you're looking at. So I have 2 different grounds. This one's very ugly, but I don't want them to be connected in this situation. And that's because I want these systems to be completely isolated from each other. So this is actually the case in our car. We have this situation where one side is high voltage power, and one side is low voltage power. So this is what happens in our vehicle, and what happens actually in almost all electric vehicles with the high voltage electrical battery. And the reason for that is mostly safety, where you don't want these grounds connected. So these are not connected at all. There's this barrier here that prevents them from being connected. And sometimes it's known as a floating system. Like this high voltage ground floats. It's not connected to the low voltage ground here. It's floating above it at some undefined potential. But the main reason is that in cars, usually you have a frame, right? The frame is the bones of the car, and they are what actually hold everything together, right? So John, please forgive me. I'm about to draw it. So this, and then like these. This, and then this is a hoop. Then you have one down here, and then you have a shit ton of stupid bars here in our car because the frame designer decided to do this.
Yup.
Is this right so far?
Yeah. Sure.
And then something, wow, something like this, right? And then you have the hoop, and then the driver sits in here, right? So there's a hoop, there's the other bar on the back of the car, and this, and then we have a little bit in the back too, and then there's wheels and stuff. But in what you do with the electrical system is you connect your low voltage ground to the chassis. So you take a wire and you literally connect it to the metal tubes. And so the whole chassis of the car is connected to this potential. The whole chassis is known as ground. So people often call it chassis ground as the low voltage power ground. And low voltage power in most cars, usually the highest voltage of that bus is about 12 volts. So that's usually because like of your 12-volt car battery. So that's like the low voltage system, and that's true in electric vehicles as well. You also have that low voltage battery, and you have a low voltage ground connected to your chassis. So if the chassis is at this low voltage ground, the driver is going to be at that same potential because he or she is sitting in the car, they're touching all the things, and so they're at the exact same potential as this ground, right? So if they're at this ground, essentially they have one hand touching this ground, right? So let's say this is a 12-volt battery of the car. This is plus and this is minus. So the ground is the minus bit. 12 volts comes out of plus. They essentially have one hand on this minus at all times because of how they're sitting in the car. So if they were to reach around with their hand, so they have a big hand here, they were to reach and touch plus, they would have a 12-volt car battery across their hands. Now, is this dangerous? It can be in the right circumstances, but usually 12 volts is not enough to break through your skin resistance. And so you can put your hands on a car battery and you'll be fine. You won't feel anything just because your resistance is high enough. That voltage is too low to break through your skin resistance. But now imagine you're doing that with high voltage power. So in a high voltage power, let's say in most cars we have a 400-volt battery, and some cars even an 800-volt. So that's coming out of plus, and the high voltage ground is minus of the battery, right? So if our driver had their hand on this minus all the time, right? If they're sitting in the car, and if the minus of the high voltage battery, the ground, were connected to the frame as well. If that were also chassis ground and these were all connected and we have one common chassis ground, then they put their hand on the plus. Now they have 400 volts across them, right? And that's very dangerous. That's enough voltage to break through your skin resistance. And you'll often get really nasty burns and abrasions. And it's even enough to kill you sometimes. And that's what we always prepare for and make sure we are taking caution with, because this is a scenario where you can hurt someone or die yourself. How likely is it to touch a positive terminal? You never know. If you're working on the car doing maintenance and things aren't set up properly, you could accidentally touch it. If some lug or wire that's attached to this part of the battery comes loose and starts flailing around, it could hit you or touch you. There are a lot of other high voltage parts in the car that could come loose as well, and accidentally you could touch. So it's always a possibility. Does it matter where you put chassis ground? I'm not sure if it matters per se. I think usually you have at least one connection to it, and you can test to see, like, the further you go down the chassis and away, the further away you are from that connection, you'll have higher resistance. So a lot of people attach more than one connection to chassis ground. But that's sort of the rule of thumb. So this is why you would separate the grounds, right? If you connect your two grounds, your low voltage ground and your high voltage ground, then you are basically connecting your high voltage ground to the frame, and then that poses a lot of dangers to the driver. And so almost every car does this. They separate them and isolate them. Mandated by the SAE rules, probably mandated by other electrical certifications needed for electric vehicles from SAE. But you need to isolate these and make sure that they never touch for safety. So how you actually communicate across, if you have different grounds, usually you have to go through isolated integrated circuits. So there are specific chips that can communicate across an isolation barrier and actually maintain this isolation as well. So they can keep the grounds separate on both sides. And still properly communicate that information over. Usually, at its most basic form, there's something you can do called like an optocoupler. So an optocoupler, sometimes people call it opto-isolator as well. So this is isolated IC, integrated circuit, right, a chip. But a very basic isolated integrated circuit is the optocoupler. That, as the name suggests, works on light, actually. So what you can do is use this chip, and what happens inside is there's a little LED. So what you would do is maybe on one side you connect it to ground, and on the other side you send your signal, right? You're sending ones and zeros. When you send a 1, and maybe that 1 is 5 volts or 3.3 volts based on your logic level, right? Let's say it's 5 volts. Light will, or current will pass through this LED. The LED will turn on, emit its light, and then on this side, usually you have a little light sensor. Sometimes I've drawn like this. I don't think I'm doing a very good job of drawing it. But basically, it's almost like a little transistor. And so when this light, when you send a high, you send a 1, light will be emitted from this diode. The sensor will receive the light and close this switch. And then now you can send your 1 across, or whatever you want to do. Maybe you want to send, so let's say this is your output to whatever you want to do on the high voltage side. Right, this is isolated. Maybe this is LV and this is high voltage side. You can connect a little 5 volts here, high voltage. So it's references on the high voltage ground. Then as soon as you send a high, you send your 5 volts, turns on the light forces the sensor to close a switch, and now you can send 5 volts out to your system, to wherever you need to go. And then when you send a 0, this switch opens up and then you don't get anything out here. So maybe you have a pull down resistor to high voltage ground or something. So this is one way. It's an optical way to transfer, for example, digital signals across. And that's often what happens in little chips like digital isolators. Really useful. Another way people do is often with, especially in power systems where you want to, this is good if you just want to send like a signal across. Like I want my 5 volts here to show up as 5 volts here isolated. This is a great way. If you want to actually be sending like power and higher voltage across, usually people use our transformers. So pardon me, current wouldn't go across, but voltage would. And transformers work on AC only, right? And transformers are isolated, right? They're just coils of wire. There's no actual physical electrical connection, but it's a magnetic connection. So there's a coupling of these wires here in the magnetic field. And so often what you can do is send your AC signal to the transformer. It will show up on this coil as well with whatever turn ratio you have. And then you can keep going to wherever you need to go. And this is completely isolated. So you can have different transformers and different opto-isolators with different isolation ratings. Usually they'll be in the kilovolt range, like they're good enough to isolate between 1 kilovolt from each end to end, for example. So if I had one side at 5 volts to ground and the other side at 1,005 volts to ground, it'd be rated to that much. For our systems, we don't go that high, but you'll see a rating of that usually. And if you want to send DC over here, a lot of times you have an isolated DC-DC converter. And inside the converter, they actually turn the DC into switching AC, move it over the isolation barrier, still AC, and then bring it back down to DC, just to do that isolation. And so you can get it across wherever you need. Is there something like that that runs on the BMS slaves? Great question. So in our car, how it works is we have a BMS master, right? BMS master. HV ground is just the minus of the battery pack. So literally, not literally ground, but so it's not grounded to like earth ground like you would do in like a building, for example. It's just the battery minus. So it's not a big ground plate or system anywhere. It's just the minus of the battery. So the lowest potential of the battery accumulator box, the battery pack. All right, so BMS master talks over UART. Hey, look at that. We know about this now. UART, and it's 2 wires, right? To BMS slave number 1. Slave. And what's important to know here is that I actually never used this feature. Wow, that was amazing. Okay, it's important to note here is that each slave is connected to the battery, right? Each one of these does 10 batteries in series, 10S. So this is all accumulator. And then you have more slaves that keep talking. So 4 in total. I ran out of space. And they all measure properties of the battery pack, right? They measure voltage, current, temperature. Now, battery pack is high voltage, is it not? Right? Battery pack is high voltage ground. You don't want high voltage ground to talk to low voltage ground. BMS Master has a microcontroller on it. It's running at voltages of like 3.3 volts off the low voltage bus. It's definitely low voltage. Low voltage, high voltage. So even though maybe your BMS slaves are only measuring 1 cell at a time, the total voltage is about 42 volts, but it's still referencing this high voltage ground, right? So what we had to do, and Jared designed this, is we had to make sure that these don't play together, right? These don't touch. And they were before in our old design. We made a mistake where we were accidentally connecting low voltage ground to high voltage ground. And so we had to make a new revision of the BMS. And what we did, and what Jared did, is not on every slave, I guess it is, but only the bottom slave that's populated, is that there's a little bit of isolation here. So actually on the BMS slave. So what he did is, if the slave board looks like this, and there's all these measurement things to talk to the batteries, and there's a little chip here to take in all that information. You zoom in. There's a few things that come from the BMS master. One is power, ground, and then UART, right? And so what he did is he put a little chip here. 5 volts comes in. Isolated chip. It's an isolated DC-DC converter. and 5 volts comes out with its own separate ground reference. And that's connected to the ground of the battery, which would be here. And then he did something similar with RX and TX. It was isolated. One side has low voltage ground, the other side has high voltage ground. And this is a digital isolator. So in principle, I'm not sure if this one is an optocoupler, but in theory, it could be little LEDs in here with little sensors, right? And they essentially just pass through RX here, and you get an isolated RX out. Same with TX. Isolated and referenced to a new ground, which we connect to high voltage ground. So in our car, to make sure that low voltage BMS master, which has a microcontroller and is connected to the low voltage system, can talk to the high voltage slaves in the battery over our UART, we have to do a little isolating. So Jared added 2 components, one that isolates 5 volt power and one that isolates the UART communication, so that it's completely safe and we can actually communicate with the battery management system slaves. So what the slaves do is they collect the information, right? You can imagine if I wanted to connect the BMS master directly to the battery, there'd be a crap ton of wires. So what we do is we sort of do an intermediate step where each slave takes on 10. Each slave takes on 10 and they have a little chip inside them on the board that takes in all those 10 and then just spits out serial data, right? So it takes all this parallel stuff and spits it out over serial communication protocol. And to the master, it turns out that's over UART. So to measure the whole battery pack, all of these temperatures, I guess not all of them, but all the ones measured by the slaves and all of these voltages, you only need 2 pins. Only 2 UART pins on your microcontroller and you can check out the whole battery pack. That's the beauty of a serial communication protocol. Any questions? We're supposed to be on the pins of SPI right now. Went on the biggest tangent of all time. But does this make sense? Do you guys have questions? It's important to understand the different grounds and isolation in the car. Right. So all of this just to say that when we was asking when would you want different grounds? Well, in our car. So LV ground to HV ground need to be isolated and not connected. So let's go back to a case where they are connected. I'm actually going to use this again. This is cool. So, please. Basically, right. I'm just going to draw a new one. So back to a simpler time. When we're dealing just in the low voltage domain, maybe we have the same ground, right? Don't need to isolate in this case. If we did have different grounds, we could put a bunch of isolation chips in between, but in our case, we don't. And we want to talk over SPI. So like we said, it was 4 lines. So slave. And slave could be anything. It could be an analog to digital converter. It could be a little battery management system chip. It could be a digital to analog converter or a current sensor. So many different applications. But 4 lines. First one is called chip select. First thing to note here, so I'm going to tack on an N at the end. Who can tell me what that means? How about Jay?
Neutral or not? I don't know. I'm not sure.
It was close, yeah. Not as good. Not as exactly right. Essentially, it just means that it's inverted, or it's like essentially passed through a NOT gate. Almost, you can think of it in your mind. And it just means, like we've talked about in earlier lessons, that it's active low. The chip select signal is active when it is low. So when the chip select signal is at logic level, so maybe 5 volts, it's not active. When it is low at 0 volts and ground, it is active. This signal has been activated, the chip select. Sometimes it's shown as a little bar on top, like this. Chip select, active low. Sometimes people also do some other things, like they put a little hash symbol here. Sometimes you get the N before, NCS. All of that means that it's an active low signal. So it's not your generic, okay, if it's a 1, it's active. If it's a 0, it's not active. It's literally the opposite. Active low. If it's a 0, it's active. Next line. SCK, serial clock. What does that tell us about this protocol, Raphael?
They're synchronized.
Beautiful. Synchronous protocol. Not UART, where you have to have a baud rate on each side, right? And you have to make sure you're reading and sending data at the exact same rate. You're sharing your clock right now. You're synchronized. Each stopwatch on each system has the exact same universal clock. And so it's really easy for the master just to decide which clock to send at what speed, and the slave will have access to that and can just read at whatever clock the master needs. You don't have to have a predefined agreement on what speed we're going to talk at, which is nice. Drawbacks, adds another wire, right? So it's a pro and con. The next 2 lines indicate to us that it is full duplex, and what these lines are called are MOSI. And MISO. Now, what's important to note is that in SPI, very similar to I2C in this sense, you're not crisscrossing anything. No crisscrossing of any lines. Everything connects to the same pin. So chip select goes to chip select, serial clock goes to serial clock, MOSI goes to MOSI, and MISO goes to MISO. So these 2 are where the data happens. They're a lot more descriptive, per se, than RX and TX of a UART communication, especially because RX and TX are a little confusing, because you just say RX, you don't know if it's your master's RX or if it's your slave's RX and who's receiving from who. Those you have to crisscross. But here, all MOSI means is master out. So it tells you where it's leaving from. Slave in. Tells you where it is going. I think I included the L here, mostly. So basically this tells you no matter who it's referenced to, or you don't have to think about if it's coming out of the master or the slave, you know this line is always leaving the master and entering the slave. And so this is the transmission line from the master. So this means that data is leaving from the master, master out, and going into the slave, slave in. Now you can imagine MISO is very similar. Right? MISO is just the opposite. Master in, slave out. These are very descriptive names for pins, more so than receive and transmit. And we need this distinction because we're full duplex again, right? I2C, we only had one data line that shared data. So MISO, master in, is going into the master, and it's coming out of the slave, right? So it's going this way. So you can see you have 2 flows of data, one going this way, one coming back this way. That's what gives us that full duplex nature, and we can transmit and receive at the same time. And that makes SPI really fast. A lot faster than I squared C, for example, where I squared C usually, the standard to max out at is about 400 kilohertz, or 400 kilobits per second. There are exceptions. There's like ultra fast mode or something random that can go up to 1 megabit per second, but in SPI, very standard to be anywhere from like 1 megabit per second up to even like 50. So it's just crazy fast, a lot faster than some of our other ones. That's why people like it so much. But again, drawbacks, right? Everything's a trade-off. You want more speed, you need more lines. You need to have these 2 data lines instead of just 1 from I squared C. So if you want a really low pin count and you don't care too much about speed, I squared C is really nice. Other drawbacks, you have to be addressing different slaves, and there's a little bit more overhead on the protocol. But SPI, if you want speed and you're okay with 2 extra pins, right? You have 4 pins total, then that's fine. Then go for it. It's a lot faster and a lot easier to use. Any questions? Cool. So with SPI, you can talk to multiple people at the same time, just like I squared C, which is cool. It's a little different. In I squared C, you had addresses, right? So everyone had to have a separate address, and they all shared literally just one data line, SDA, right? And the way each slave knew if you were talking to it was through its address. If you said, hey, Faraz, then Faraz would know to reply. If you said, hey, Samarine, then Samarine's address would be activated, and then you can get data from her. In the SPI case, it's a little different. You don't have these addresses. What you have instead is your chip select line. Some people also call it slave select, but chip select is really popular. So this is slave 1, call it S1. Slave 2, S2. Each one of these has all the pins, right? So let's draw a serial clock. MOSI, ISO, and chip select. Same with our other slave, right? That's just the interface for SPI, so that's what they come with. Okay. Did I put MOSI first? Yeah, I did. MOSI. So what happens is SCK, serial clock, MOSI, and MISO go to everybody. They all get a copy of that line. So this will go down here. This will go down here. And MISO also comes here. But the chip select is where we separate, right? So just quickly. Your slave will have more than one chip select. So they'll have chip select 0, maybe, then chip select 1. So these are 2 separate pins. So that's another addition to the number of wires, number of pins you're using from SPI. It's going to add every time you have an extra chip select. And you'll have an extra chip select for every slave you talk to. So I'll have 1 chip select going to slave 1. And then I did not number this properly. So let's call this slave 0 and slave 1 down at the bottom, just so it lines up with our chip selects. Cool. So we had 1 line going from chip select 0 to chip select of slave 0, and 1 line going from chip select 1 to chip select of slave 1, right? And what happens actually is that if I want to talk to slave 0, all I need to do is engage chip select 0, And the way we engage it is an active low signal. So we're gonna send a 0 on it to ground. Then this slave knows to start listening. It said, hey, here's my chip select. I've been asserted, sometimes they call it, or I've been activated. My chip select line has gone low. That means I'm the chip that's been selected. Lucky me. Now I can listen to all the data on the line and do whatever I need to do. You know, slave 1 is the unlucky son of a gun where it's listening for its chip select to be selected. And unfortunately, it wasn't in this case, right? Chip select never went low. It just stayed high. Chip select 1. So unfortunately, slave 1 doesn't get to do anything with this data. It's obviously going to see it, right, from afar. All this data still comes into here. It's just that slave 1 doesn't do anything with it, doesn't reply. Kind of looks at it very sadly. But slave 0, since it's been selected, gets to have all the fun and gets to communicate and do whatever it needs to do, send data. Then when it's done, this chip select will go high to deactivate that chip. And then maybe it's this one's turn now, right? Maybe chip select 1, it's one's turn. They'll be activated by going low. Now slave 1 can communicate over these lines and do stuff with the data that it's seeing there. And so you can see it's a little different from I2C, where in I2C we had, here we have so many lines, right? We have 2 data lines and a separate chip select for each slave we want to talk to. In I2C, all we had was one master. All we had was one SDA line and a clock line. And this SDA line went to everybody, all the slaves in the neighborhood. I guess the clock too as well. And the way we talked to different slaves was by giving them an address, right? Each one had its own unique address. And I would talk to the second one by sending the second one's address, right? So you can imagine you're shifting this data of identity between hardware, where you have actual wires selecting the slave, and built into the communication protocol, the identity of the slave. So it really depends on what you're looking for, right? If you want a faster solution and you don't care about having extra wires, SPI, and you have a lot of things on that same bus, SPI is great because you can just send a chip select to whatever slave. That's fine. But this will add to your pin count on your microcontroller, and that can be expensive. It may cause you to have to buy to switch to an even larger package with more pins. So if you're really worried about pin count, then I2C is really nice because you only need 2 pins and it stays that way, which is cool. Any questions? Cool. So let's look at an example maybe of some data that might go across an SPI bus. So there are a bunch of different modes, which we'll talk about in a second, but let me just pull up a picture here. Cool. So this is sort of what an SPI communication data burst would look like. So slave select, chip select, same thing. And you notice here they use that hash instead of an ed. Again, active low, that's all that means. And that's usually how, usually how all these communications start. Your chip select or slave select will go low, and that starts the whole procedure where you've actually selected the slave to talk to. The next line you can see is your serial clock. So this is what a clock looks like. Maybe we've referred to it a lot of times. I haven't really explained what that means. It's just a little a little train of pulses. All it is zeros and ones toggling. And the frequency of these signals is basically referred to as the speed. So if I'm toggling the clock at 1,000,000 times a second, 1 megahertz, it's going up and down. That means the period of each one of these little things is 1 microsecond. So that would look something like this. So from here to here, and then it would start again, right? That whole thing is about 1 microsecond. So it's really, 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 really tiny. And you get to control that. As the master, you get to decide what speed you want your communication to occur at. And usually you're going to look in your slave's data sheet, right? Your slave has some needs, or your partner who you're communicating has some needs, and they need to need those needs to be satisfied. You can't always just send whatever speed you want. You have to take things slow sometimes. Sometimes you can crank the pace up. But they're usually going to give you a window in the data sheet that says, hey, bud, I know you can control the speed, and I'm cool with that, so you can do whatever you want, as long as you're sort of in this window that I can accept, right? Maybe that window is anywhere from like 1 kilohertz, for example, to 20 megahertz. I just made that up. It can be very different for whatever chip you're talking to. Usually they'll give you a window. A lot of times there won't be this bottom side, so you can go as slow as you want. Slower is easier for me. But definitely the faster side, there will be an upper limit. So you got to look at your data sheet to make sure you're not going too fast, so that you can make sure that communication actually is received properly by the slave. Next thing we can look at is MOSI. So remember, master out, slave in. So this is coming from the master. And a lot of times it's some instruction, like they say here. So you're sending something, and that's going to be some data, right, of zeros and ones toggling back and forth. So for example, this would be a 1, this would be a 0, this would be a 1, this would all be zeros. And the way you know to sort of split those up is by how fast your clock is going. So one period of the clock, for example, one period of the clock would be 1 bit of data. So you'd have 1 bit of data here. And then another period of the clock would be some other period of data, some other bit of data. And based on how fast your clock is going, then these will grow wider or shrink smaller. Basically the length of your ones and zeros. So your clock defines how fast they go. But at its most basic, MOSI will spit out some info, and then MISO will come from the slave back towards you. And what's cool is that you can do these at the same time. So what often happens is the first instruction you send, right? You're going to send some instruction. There may be some data coming back here, but it just might be garbage at this point since you don't know what's going on. But you send some instruction, you say, I want to read your ADC values, right? Say I'm talking to an ADC. So ADC. ADC, get rid of this S. Little chip. And it's spitting back to me voltages that it's read. I can ask for it to do that over some instruction. And then the next time I ask for data, it will have sent what I asked for previously. It can't give me what I want immediately because it's still receiving that data as I'm sending it. So it's important to understand is that SPI controls all transactions. You're not going to get, the master in SPI controls all transactions. The slave can't decide to send data whenever it wants. It can only send a burst of MISO data as long as MOSI is sending it some stuff, right? So if I'm the master I can send some instruction out on MOSI line. I send some data, and at the same time, I'm going to be getting data back on the meso line this way. So maybe the first time this doesn't really mean anything to me since I just powered up, but maybe this is an instruction that I say I want to read voltages. So I've sent this instruction, and this is all going to my slave, right? Just go up here. The thing is now I can't just chill. I've asked it to read voltage, but I can't just now wait and expect it to send voltage after, which is a kind of a peculiar quirk of SPI, but you have to basically ask it something else. You have to keep it talking. So I've said, I want to read voltage. At the same time, I've gotten data back that maybe doesn't mean anything at the start. But now the ADC has received that, okay, my bud wants to read voltages. Maybe I should do that. And so for the ADC to do that, the master actually has to send something else next. Has to send another burst of data. So maybe 5 milliseconds later, MOSI maybe it just says the same thing. I want to keep reading voltages. That's good. Keep giving it to me. Now that the ADC knows it wants to read voltages from before, right? We said, so this is earlier in time, so time is progressing this way. ADC knows it wants to read voltages, it's just waiting for more data to come so it can send, right? So as it gets its second message, oops, ADC, as it gets its second message, now it's actually sending those voltages. So maybe this is like 4.5 volts. And you're getting this data at the same time as you're sending the next message. So you can almost think about it as a little bit of a time delay. So I say, I want something to happen. ADC kind of understands that message and says, okay, next time you ask me for something, I'll have what you wanted from before. So you say something else, okay, maybe it's the same thing in this case. ADC will have that voltage ready to send to you, and you're receiving that at the exact same time on your meso line. Note that you've asked for read voltage twice now, right? You said I want to read voltage, then you sent it again so that you can get that data. The ADC has now seen that you want to read voltages twice, so the next time it's also going to send you that voltage. If you ask for it twice, it'll give it to you twice. Right? It'll give you... It's supposed to be the same. It'll give you back that voltage that you asked for. And you're like, great, I did ask for that twice. Thank you very much. But now this time, for my next transaction, I don't want to read voltage, I want to read current. Right? You're still getting back the voltage you asked for, which is great. But now you can already start preparing and say, no, okay, next I want to read current. That'd be really useful. And this is all happening at the same time. You don't need to share one line and say, okay, on one line I want to ask for voltages and then get voltages back, and then ask for voltage again and get voltage back again, and ask for current and then get current. The first one is a waste because the ADC doesn't know what you want yet, right? So this very first one that you get back is probably garbage data. But after that, you can do everything at the same time. You've asked for voltage, the ADC will give you back voltage. You ask for voltage again, the ADC will give you back voltage. At that same time that you're getting back the second voltage, you can already start asking for current. You can say, good, give me the voltage I asked for, that's great, it's really useful. At the same time, I'm preparing you now because I want to read current next. And so you can keep sending messages and getting more data. But the main key here to remember is that the ADC will not send anything back unless you have initiated a data transfer. You need to be sending stuff to it for MISO to come back as well. And sometimes that, let's say you say, I want to read voltage, and there's a command in the ADC where you only have to do it once, for example. You can set like, I want to read voltages and just keep sending it to me forever, right? Maybe I just want to say read voltage forever. And it definitely depends on your ADC datasheet and what messages are available. But let's say there's a command that looks like this. You can send that to the ADC. ADC is happy. It's sending whatever it was before. So this would be current now, right? The current data. Maybe 5 amps. 10 amps is easier to read. You don't always have to send it real commands. You can just start sending garbage after this point. You've told it you want to read forever, so it knows whenever it receives the MOSI input that it can just keep outputting data. So next, all you can do is just, and what we often do is just send all ones. 1, 1, 1, 1, 1, 1, 1, 1. Just garbage data. And all we care about is what's coming back. But we still have to initiate this data transfer. We have to do something here, whether it's garbage or not, just so that the ADC will send stuff back. And this is a property of SPI. The master will control all data transmission. It will decide if MISO is activated to send stuff back or not. For your slave to send data back, very first thing, chip select has to be activated, right? And then MOSI needs to be sending some data bursts so that MISO can send stuff back as well, whether MOSI is garbage or not. And don't forget, while all of this data is happening, your clock is toggling happily all the time. If your clock is never not toggling, if your clock is never not toggling, no, if your clock is not toggling, then you can't have any data, because that's what synchronizes all the data bursts. Questions?
Do SPI devices in general have like certain clock speeds that they want, or are they just gonna conform to whatever you're sending?
A lot of times they'll conform, but like I mentioned, there will be a range. Usually, it's rare that you see a device get angry if you go too slow, because slower is easier. Faster is harder because they need to sample fast enough to actually catch your clock rate. If you're toggling too fast and it can't handle it, it's just going to miss a lot of pulses. And so it'll get a bunch of garbage. But I'm sure there are some devices out there that beg for a specific frequency. I just haven't used any that are that precise. Do you have any, Junaid, in mind that are like that you've dealt with before?
SPI. ADC.
Does it ask for?
It doesn't go below 20 mega. You
does
can try
though.
below. You've tried it?
It works at 2. It works at 1.
Oh, you tried it with 1 as well, and it worked?
Yeah.
Nice. That's the only one that I remember.
Yeah. Yeah, it says max 20 megahertz in that data sheet. But yeah, I tried it with 2 and tried it with 1, and it works great.
Nice.
More questions? So we use SPI a bunch in our car. A great application is the thermistor expansion board. So basically what this does is it measures temperature. Right, we've talked about this board before. All it is a bunch of multiplexers and an ADC that basically send a crap ton of wires that all have a variable resistor. And this resistor will change resistance based on temperature, right? So it's a super cheap way to measure temperature. So all of these go through some multiplexers. So like 8 signals come in and only 1 comes out. And a bunch of them then go to an ADC. Right, we've talked about this. So it samples all of these analog voltages from the changing resistance and then sends them over digital over SPI. So we use SPI in this case, and we send a bunch of commands to the ADC. We say, I want to read this, I want to read that, I want to configure this way. And the the ADC will send data back on the MISO line, giving us all the different values of voltage drops on these. Then, because of some great code and drivers written by Yash and Jazz, Junaid did a lot of work on this as well. Then we can convert all these voltages across these resistors into temperature, which is really cool. So that's how we measure all the temperatures in our battery pack. Another application is from the ECU to the high voltage board. This is a board that Braden designed. What this board does is it samples the overall high voltage bus to see what it's sitting at. So there's a bunch of circuitry here, isolation, very important, high voltage. So it's measuring high voltage plus and high voltage minus. And then it has a little ADC. So the ADC. And what's interesting about this one is it's only 3 lines. So that ADC is serial clock. Sorry, chip select up top. First thing always. Serial clock and MISO. So this one's a little special. So all it does is as soon as you engage chip select, it just spits data out on MISO. This one's a little different. It doesn't actually want any commands so it's very basic as an ADC. You can't ask it for anything. You can't set values to configure it or program it. It just spits out data and that's it. So to actually engage chip select in our code base, to actually assert this low and start the clock to send data, we don't actually do this manually. We don't say, all right, set chip select to low. Now for clock, go 10 10 10 10 10 10 really fast. We don't actually do that. All we do is the drivers take care of that for us. So we just say start SPI. And then once it starts, then what actually happens is MOSI will send some fake data, just all ones, which will start the clock sending, and then the ADC can spit out data back to us. So that's a very specific case. Any questions? Looks like we have controls meeting. A few other things we can talk about, but we'll do next week, are some of the modes of SPI. Basically, which edge we're sampling on, and the value of our clock when it's not sending data. But those are specific to each chip. Questions? We need 3 before we can go to our meeting. Raphael, any questions? Yeah, good question for us. The 05H. So the very observant, I see. I'm trying to gloss over things, okay? Please, let me be vague. So instruction 05H, that's basically what the value of the data they sent this specific case is. It could be anything that you're sending. You could send whatever you want. So this instruction is probably something specific to the datasheet of the slave or ADC that says if I get a 05, then I should do X or Y or send Z. But all this H means beside it that means it's hex. So 05 in hex. So 05H. What this H tells you is that you're looking at hexadecimal format. In hexadecimal, each of these things are 4 bits. So this means a 0, 0, 0, 0, 0. And the 5 is 1, 0, 0, 1. So 2 placeholders in hexadecimal mean an 8-bit signal. So this is just some instruction that it's sending across for the slave to do something. And what's cool is that in SPI, it doesn't matter. You can decide if your slave wants it, you can send 24 bits across, you can send 8 bits, you can send 12 bits, you can send 16. There's no specified standard like we had where UART we sent 8 bits at a time, right? And in I2C, we sent, in I2C, we had to send like a 7-bit address, and then we had to do a read or write bit, and then we had to have an ACK, and then we had to get the data from the slave in 8 bits. This was this whole complicated thing for I2C. But in SPI, it doesn't matter. I can just send 12 bits of whatever I want, which is really cool. There's no addresses, there's no ACKs, there's no read-write bits, there's none of this. As long as your slave knows what you're doing and your slave is asking for this stuff, then you can just send whatever formats you want. How many chip select pins are on the average SPI interface? I think in the TMS570 on the VCU, there are about 5 different actual SPI peripherals on the TMS570. You have 5 full SPIs. Some of them are special too. And then each of these, actually not all of them, but some of them have 2 to 3 chip selects. Maybe even one of them has 4. But yeah, that's usually it. If you really want, you can just use another generic GPIO to be a chip select for you. Right? You disable all of your normal chip selects, and you just get another GPIO pin, just any generic pin, and you can use this as a chip select to a new slave, and just manually assert it low whenever you want to talk to it. Good question. All right, last one. We've gone 2. Jade, give me a question. I dare you. Ask me anything.
Which type of serial communication protocol would you prefer to use? I guess.
Oh God, I don't know the answer to this one.
Well, I guess which ones we use most in the Phantom car?
Yeah, yeah, good question. I'd say this is one of the more popular ones. I think we use it three times. Yeah, Junaid, I know I asked for any question. Doesn't mean I can't answer any question. So we've talked about a few. You are maybe up there. I like SPI just because it's fast and it's relatively simple. You don't have all that overhead of addresses and ACKs and rewrite bits and data and then another ACK. And then if you don't get an ACK, you have to restart all in one data line you're sharing to go back and forth. And I2C, you have total freedom. You have a send line and a receive line. It's very clear. You don't have to crisscross them or anything. But whatever your slave wants, you can just send it to them. There's no overhead or anything. So we use this 3 times in our car. UART is theoretically 1. Theoretically 1 to the BMS slaves. We also use it to the computer, which is not really in the car, but to the computer, like over USB. There's a USB to UART converter we use. Passcode is only 1. I like this one. SPI is more annoying for electrical people with all the wires. Yes, very true. More wires to route. Sorry, guys. Definitely true. How are we dividing the embedded teams now? Good question, Yash. Mahmood will discuss it in the Zoom meeting. So if everyone can click on this link in the Zoom chat, we can pop over there, and the master will begin explaining what's going on. Thanks, everyone. Sorry for going over time.